Yeah, I'm sorry, I had my sound turned off. Any other questions? I marked people. I put a Dropbox, and there was a pre-lab, and I marked them. Yeah, do it. Go ahead. If you can find it on D2L. So you will be able to find it on D2L. You just go to assessments, pull the assessments down, find the Dropbox, and you'll find that there's a Dropbox there with an exercise. Look, 11 people have submitted, and I marked 11 exercises. And so what I do at the end of the semester is I just add all of those up, divide them by the number of exercises. That's your mark. And then that mark goes in for assignments or labs. If you do the lab, yeah, I mean, you're going to get a passing mark, right? So the people that don't pass those labs, that's because they didn't hand them in, right? If you do it, yeah. I mean, it's really just to give you some work to do. That doesn't sound right. To train you in sort of doing work is a better way of saying it. So we've got 2 things to look at today. Let's look at this PDF here. Now, I can probably download that would be the best thing to do. So I'll download that, and then I'll download the other one so that we can work on them. Sorry, it's taking me a bit to get started. We will get started and we will go. All right, so I've got another one here, which is this one here. I like that better. So that's one of the other instructors added some nice stuff to it. And so we're going to have a look at that. So this is our first exercise. Now, as I said, there are notes that go along with this. All right, they are on D2L. You could follow along if you wanted with your notes open on D2L. There, if I go to that, so they're in the news, and you'll be able to sort of just follow along with the news. You can see some notes that would help you to sort of explain what's going on here. All right. Did I start recording? I don't know. No, we are started recording, so away we go. All right, so let's look at, can't hear you, still can't hear me. I got this turned on. I mean, I don't know if okay, so, right, maybe it was pointed away from me. All right, so let's go. We're recording, so let's go. Where are we here? Elements of computer architecture. So in this lesson, we'll focus a little bit on the CPU, but also on other components of the computer itself. So let's go and have a look at that. We've got a question there about artificial intelligence. Is that smarter than humans? Now, computers can do things a lot faster than humans, all right? So that's nice. But the only thing that they can do is so far is to do whatever humans have programmed them to do. We haven't actually achieved artificial intelligence. I think to say artificial intelligence, we would have to say that the computer is self-aware and is able to do general purpose problems without any sort of priming, without us giving them an algorithm as well as a human. And that is kind of, there is research going into coming to that conclusion. So neural networks is the, I think the area that they're working on to bring that about, but it certainly hasn't achieved that yet. They can do things very, very fast. They're very reliable and precise, meaning that you can do the same calculation and get it right every time, which is kind of hard for people, saying with different numbers, same calculation with different numbers and get it right every time. Once you set the computer to get the calculation right once, it should be able to repeat that every time. So that's very, very good. And as it says, if they don't get tired, you can run them until they burn out or whatever. They don't get tired. Now the idea of it being superpowers, as I said, you can refer back to his. It's got a bit of a note there about superpowers or magic. But the idea being that well, yeah, you as a programmer can sort of extend yourself, your own intellect, your abilities using the computer. So the computer is like something that gives you a lot more power. Just like when you get in a car, you are driving it, but you're going a lot faster than you could run. So likewise with a computer, but you still got to drive it. And likewise with a computer, you can do a lot more, a lot faster. Now the sort of the analogy that's given in this lecture with the computer superpowers, with the Power Rangers or whatever they were. I don't know, they come together to make one big powerful thing, but they got a lot of separate sort of powers. I think you'll see that in a bit, right? So that's mentioned there somewhere. Yeah, so on this question, what are the limits of computing? There's some notes about the limits of computing. And there's some problems that are not computable. And we've got a few examples of problems that are not computable, I think, that are in our lectures. Or do we? Maybe it's down here a bit. Non-computable problems. There was a mathematician in 1928 that sort of said, is there a non-computable problem? Is it possible that there's something a computer couldn't compute? There was this very smart mathematician. His name was Turing. We mentioned his name before, right? Turing. And Turing sort of said, well, yeah, I think there is a non-computable problem. Imagine that you have two programs, program A and program B. When program A is running, program B is not. And every time program A stops running, then program B starts running. So program B, and they're the kind of the opposite of each other, right? Now, what if you had the ability of a program to call another program? That's quite possible. We have programs that call each other. Then what if you had program B call itself? Then what you'd have a situation of is program B is running and not running. All right, so that is non-computable, and it's kind of almost like quantum mechanics problems. And actually, some people say that the solution to that is to use quantum computers. But Turing in 1936, he put that theory and basically said there are some things that are non-computable. There's some other things that are mentioned. If I think, again, you can find these in the notes. I'm looking for the sales, the traveling salesman problem. Okay, yeah, the halting problem is kind of related to that. Halting problem, is it possible to know when the computer will stop? And that's basically what Turing was working with. Something related to that is working with prime numbers. You know what a prime number is? It's only divisible by itself and the number 1. And so we have a list of prime numbers. Now, we can have this thing called a secondary prime number, which is basically a fact. It's only divisible by itself, one other prime number, and number 1. So it's not exactly a prime number, but it's kind of related to it. Now, we can use those numbers for special things. So you can compute a bunch of these, and you can go to like 100 decimal places with these numbers. And then you can use them as numbers that are hard to discover, that you can use for special purpose. The special purpose that we typically use them for is we use them for a key in encryption. Now, encryption means to take plain text, something that people can read, and turn it into gibberish, kind of. It looks like it's random, but it's not random. What we've done is we have run we've multiplied the numeric sort of equivalent of each character by the key, and come up with something different. Now, unless you've got that key, there's no way you're going to understand what that message is. We use that all the time. So we have keys. We have 128-bit keys. We have 256-bit keys, and they're virtually impossible to break. Now, when I say they're virtually impossible to break, we started off with a 64-bit key, and we found that with computers, we can, using a brute force sort of crunching, we can actually break that key. 128 was harder, but not hard enough. And so they introduced the 256-bit keys. Yes, you have a question? The language of computers only uses 0 and 1, correct? Sorry? Yes, but so what we have, and you'll see this in lecture 4, when we talk about computer programming, we have to have some way that we can program the computer. We don't talk in 0s and 1s. So we have computer languages where we can sort of interface with them and using instructions that we can understand. Then we have a special translation that's going to take our instructions and turn it into 0s and 1s, which is what we call the machine language, so that the computer can understand it. Yeah, all right. So are you okay with the idea of having big numbers that we use as special keys that are hard to compute? And this was related to the can we have a problem which is uncomputable? The idea is we have these numbers. Yeah, we could compute them, but maybe it'll take 100 years, right? Or maybe it'll take until the end of the universe, right? But it's very, very hard to compute these numbers. And that's what gives us security. We like that, right? When we're doing our transaction with the bank, we're moving monies around, we're buying something online. We want to be satisfied that somebody else isn't out there and intercepting our transaction, and then intercepting that transaction and crunching and finding the numbers, and then having our passwords and stuff like that. And tomorrow they clean out our bank account. That would be very bad. We don't want that. And so we have to have some kind of security. The security we use is these very, very hard to compute numbers. Does that make sense? So it's not impossible. It would just take a long time using the way things do. And the beauty of it is, okay, so you get more powerful computer that runs a lot faster. Maybe we can compute these numbers faster. Fine. What we do in the security side of things is we just compute a harder number to start with. And so we always try and stay ahead of the bad people that are trying to get our numbers from us, right? You may have heard of Bitcoin and stuff like that. They're not computing numbers. What they're computing is this thing called a blockchain. But you can think of it as sort of like that. What we're trying to do is we're trying to connect pointers that go from one sort of block of code to another to get something unique. And then that thing, we put a value on it. We say, that's mine. I own this thing. And it's now worth, I don't know, $45,000 for one Bitcoin, right? And the Bitcoin is what? It's just sort of a number in a computer somewhere, right? And that's yours. And because it's very, very hard to compute it. Now, how hard is it to compute it? Let's just give you an idea on that. China has made that illegal. There were a lot of people that were doing what they call Bitcoin mining. I don't know if you ever heard of that. So they're using big computers and they're trying to generate these blockchains. And it used so much power, so much electricity that China didn't like it, right? You know, why are you spending all that just so that you can personally get rich? We don't want you doing that. You're not going to be able to do it in China. And of course, China has authoritarian government. They can do things like that. They can say, you will not do this. So these people have to leave China if they want to do Bitcoin mining. Anyways, one day you might be interested in that. Some of you might do data security, crypto security, which is, we have a degree here, right? All right, so computers do anything? Oh, well, this is cartoons from a syndicated cartoonist. His name was the cartoon. I don't know what his name is. The cartoon was called Dilbert. If you want to have a bit of a laugh at this, the idea of Dilbert was an IT guy. The guy who actually did these cartoons was an IT guy working in a large organization in the United States, right? So, and his cartoons are always making fun of the management and the people that IT people have to work with, but also making fun of the IT people. All right. So if you want to, basically laughing at themselves and laughing at other people, you know, all the stupid things that people in businesses do. And so this is one of the stupid things that happens in business. The IT person wants to make a computer program for their user. So the IT person goes to the user and says, okay, so what do you want in the program? And then the user says, well, why don't you tell me what I should have in my program, basically. It's funny to IT people because, as dumb as that sounds, it's kind of what happens. And especially because you develop something for them and then they look at it and they go, oh, maybe we could do this and maybe we could do that. And so you often end up with something in the end, which is totally not what you thought you'd do in the first place. Hopefully you're familiar with this term software. If you're not, it's okay. Basically, you could say that if you got hardware, which is the stuff that you can touch, that gets hot, that you put electricity into, that works for you, you have to have some instructions to make it work. That's the software. All right. So the software is going to be your computer programs. They're typically going to be put together in an algorithm or sort of based on an algorithm. What we do is we design the algorithm. From the algorithm, we then code it into a computer program, and the computer program is executed. We call that software. So here at the college, we have degrees and diplomas, which are basically divided on that way. You can do something which is a hardware degree, so a degree in networking and computer hardware. So that would be if you wanted to put together computer networks, cabling, installing and configuring devices, that would be working with computer hardware. The other thing that you might do is a computer software thing, which is developing websites, computer programs, maybe apps for phones, things like that. That would be a software degree. All right, so we okay with this? So far good? Just continuing on, you see a lot of different components. And again, as I said, there are notes for all of this that are there. These things here, if you see any of these links, that's a video for you to watch. So I mean, I don't have time to go through the videos with you here. Do that at home. These links here will take you to, most of them will take you to like a Wikipedia article. I mean, you could spend a lot of time learning this stuff, which would help you, I suppose. If you opened up one of these boxes, these things would be in there. The most important, I guess, central part there is the CPU. CPU for the central processing unit. CPU, do you notice that it has a fan with it? The fan is a heat sink. It's part of a heat sink. The problem is that the CPU runs fast, produces a lot of heat. This is a big problem for computers. We need to get rid of that heat. Inside the CPU, we have the arithmetic logic unit and the control unit. We'll have a look at those in terms of a model. The CPU is going to fit into a slot like this thing here. You'd take that CPU and just plug it in there. That slot would have a bunch of pins that pins on the CPU would connect to. So then those wires would go out to the rest of this. This is called the main board here. Some people call it a motherboard. So the CPU is going to be connected to everything in the motherboard through wires. We call those wires are actually kind of like printed into the motherboard, and they are we call those bus. We call those buses, and there's more than one bus. So you got a bus that goes to the memory. So here, these slots here are going to be your memory slots. So into your memory slots, you put random access memory, so you can expand it. Now, in a lot of more modern CPUs, and especially in your laptop, it's not going to be quite like this, right? I mean, you're not going to have slots there to add extra memory. The memory is soldered into it, right? And so to save space, and so especially, you think of like your MacBook Air, right? What slots you got? Everything is sort of soldered into it. It's a one piece, and so you buy it. You get the specification when you buy it, and they put it. They give you something that's pre-made with everything sort of slotted in. But if you have a build your own computer type idea, you can usually expand into it. So we have some other expansion slots there. Adding RAM cards, this is a card, is one of the easiest way to speed up a computer. But as I said, nowadays, what you're typically doing, because most of us are using laptops, is you will just order it like that, or you'll buy it like that with a certain amount of RAM. You're not going to be able to open up your laptop and add extra RAM, probably not. But if you had a desktop like this, you could add some extra RAM. Other things that you can add and change in and change out is a VGA card. So your visual graphic, I would call it adapter, but they've got another name for the A. Have a look at that, what they call it. What's their A? Visual graphic. There it is, VG card, graphics array. Yeah, okay. So yeah, all of these things are described in that. Notice that the VGA card has got also a heat sink and a fan to take the heat out of it, because it has a processor on it, and that's going to be your graphic processor. Is going to be on the VGA card. We have a processor like that on most of our modern computers because people are using them for things that are intensive use of video. So people are watching Netflix, but the other thing they're doing is they're playing video games, right? And they don't want the game to go slow and lag because the video card can't keep up, because then you start losing the game, right? So any of you who are gamers, you spend money, get extra money to have it extra fast. One of the things you do to make it faster is have a fast video card with a better graphics processor on it. Sound card. Now, as I said, a lot of this stuff will be actually built in on a laptop. That's just going to be built right into it. Your hard disk. So the word disk, yeah. Again, most of us are using laptops. If you got one of these really thin laptops, it might not have a disk in it. It might just use SSD, which stands for solid state. Okay. So your solid state drive is going to not have any spinning disks. This one here, I think you can sort of see there's something there that looks like a circle. The way that we did our data storage was on a magnetic disk that spin. And well, it was more than one disk, but they were in a platter, but it would spin. And that's still the cheapest way to get it. So you may get a laptop that's got that in it. But you pay a little bit extra, you get an SSD. The SSD is faster, has no moving parts. It's all just sort of transistors on a card. Yes. Quite possibly. Yeah. Yeah. Okay. So this is just input output. So maybe you want to take your memory cards from your phone or from your camera, and you want to read them. And there's some more input output there. I think that's enough on that hardware stuff. Okay. Yeah. Tomorrow we'll do a tutorial on binary to hexadecimal to decimal. So we'll spend a lot of time talking about that. But here it is in this lecture. Binary is only two things. Bi means two, binary. So we only have two numbers that we can use in binary. That's 0 and 1. So everything is a combination of 0 and 1. But we can put them together to make bigger numbers. And you see that in the notes. In the notes, it says, okay, so if you only got 0 and 1, you can only have two states. But if you put the 0 and the 1 beside each other, then you can get 4 states if you have two of them. So you can have 0, 0, 0, 1, 1, 1, and 1, 0. And if you put 3 of them together, you could have 8 states. If you put 4 of them together, you could have 16 states. Each time we're multiplying by 2. And so this is, we'll spend a bit of time talking about that next lesson. All right. How are we going? It's all right? Doing good? Yeah, all right. Programs are stored in RAM. This is the fetch, decode, execute cycle. The RAM is separate from the CPU. The CPU has to get the program from the memory, from the RAM. Random is random access memory. Then it goes into the CPU. And when it's in the CPU, then it has to be translated. I guess you'd say decoded is the word we use. So we decode it into zeros and ones so it can understand it. And then it will be executed. When it's executed, it may have to get some data to go with the instruction. So during the execute part of this cycle, we'll get data from, that'll also come from memory somewhere. And also inside the CPU, there's some special memory, which we refer to as registers. And I think we've got a diagram for that. So yeah, we have RAM, random access memory. It's fast memory, but it's outside the CPU. We also have some memory inside the CPU, but the fastest memory outside the CPU is RAM. Now, we have storage memory, right? That's on our transistors. And we would have a SSD or else a hard disk. But the RAM is actually even faster than that. Mind you, SSD is pretty fast. So we have this fetch, decode, execute. Let's have a look at how that, oh, well, yeah, let's look at this. This is a comparison of two different ways of making or imagining a computer. The top one is Van Neumann, which is the model that was imagined by Van Neumann. Susan. Short memory card. Yeah, you're right. I think you're referring to this diagram. So this thing here, yeah, it is a short card. And if yeah, so and it fits into this slot very close to the CPU. So we have two different architectures here. And as I said, these are theoretical architecture. The one on the top is a Van Neumann architecture that is used, according to our notes, in computers like your desktop computer here is going to use a Van Neumann architecture. Van Neumann architecture is very flexible, and so it's used in that type of way. What is different between that and the Harvard architecture is I hope that you notice that the Harvard architecture has actually separated the buses that go to the two different memories here. So we've got a data memory and a code memory. We've separated them away from each other. Okay, so you're going to separate the code, which is your instructions, from your data. And you know, they might be in the same physical device, but you're going to put the data and the instructions separately because we don't want to mix them up. But what we actually do with the Harvard is we make that physically separated. You cannot have, so we're separating our data and our instructions from each other physically and actually having a different bus going to each one. And so this one here, I think you can see that it's a little bit different. It's going to be faster because we're not using the same bus for multiple traffics. Each bus only has kind of like one job, right? Instead of over here, you can see this bus is, it's going to the data code memory, it's going to the data memory, and it's going to the CPU. Here, that bus is just going here, CPU to data. Okay, got the idea? I don't know if you have to memorize them at all. I don't know if you have to memorize them. Just know that there are those buses there. Know that the Van Neumann architecture gives you something that's more flexible, and know that the Harvard gives you something that's faster. And then know that the Harvard is used in things like mobile phones and things like that. It's used for special purpose devices, whereas the Van Neumann architecture is used for general purpose devices like your computer. I think that's all you need to know. So here's the fetch, decode, execute cycle represented in a model. And so I would start down here in the bottom left and say, we have an instruction in the main memory. We've got an instruction in the main memory when we load a program up. We load the program up, instructions in the main memory. It's going to take the first instruction, and it's going to see the arrow is taking that instruction and it's putting it into the CPU. So that's called the fetch. It's fetching the instruction. And then as part of that, it's going to decode the instruction and put it into zeros and ones machine code, if it has to be. Now, the green stuff there, registers, is we might have some temporary memory where we have to do something with this instruction to relate it to the ALU, all right? And likewise, we might have something coming the other way. Now, then the next part of the cycle is the execution. There we're going to get any data that we need to use with the instruction, and then we're going to execute the instruction. So we got 4 steps. 2 of them happen in the fetch, where we fetch and decode. 2 of them happen in the execute, where we get the data and execute the instruction. During all 4 of those, we might be using these registers, which is memory that's inside the CPU, to hold data or instruction for a short period of time between these two parts of the code. Of the CPU. Then when we're finished executing the instruction, often there'll be some output from that, which we could then store in the main memory, and then it could be sent to some output device or something like that, right? So afterwards, that's what that arrow there represents, is we finish the instruction, we store that back into the main memory, whatever was the result of that instruction. All right, here we go with the Power Rangers. The Power Rangers here representing you being the superhero. You're the superhero, which is the single cycle processor. The idea is that from us looking at what a computer does, it just seems like there's one thing happening. But in fact, there's 5 things happening, right? We're fetching, decoding, executing memory, and right back. And only when we put them together do we get the super. Did you guys ever watch Power Rangers? I'm too old for that. Sorry, I did not see it. But apparently that's how it goes. Some other people told me. And the last slide on this, thank gosh you're saying, me too. Imagine that you're cooking, and you're cooking, but you don't know what you're going to cook. So you go to Google and you put in the whatever it is you want to cook. Like, I want to cook brownies or some cake. I want to cook a pink cake, and so a pink cake. And then when I do that, Google, it comes up with a recipe for pink cake, right? And there's ingredients and there's instructions, right? So when I go to Google and I search for pink cake, what I'm doing is I'm fetching, and comes up on my screen is this instructions on what I need to do, right? And then I have to think about that. That's the next step there. Okay, so I have to look on the computer and say, oh yeah, all right, so to do this pink cake thing, I'm going to need sugar, and I'm going to need flour, and I'm going to need pink coloring, and I'm going to need some other stuff. I guess some yeast, I don't know what, baking powder or something like that. I'm going to need all these things. And so I'm probably going to go and get them. Hopefully they're in my kitchen, but I might have to go to shopping at Mira or something and get those things. So that would be my decode. Actually, yeah, that would be my decode. Actually, when I do the execute, I'm going to get that stuff. Sorry. Here I know that what I need to get in my decode. Then lastly, I'm going to go and make the cake. That's my execute. Actually, does that make sense? So we're doing the fetch, decode. Now, actually, this thing here, getting the ingredients from the store would not be part of decode. That would actually part of execute according to our other diagram, right? Because if you, so sorry about that. We get the data in the execution cycle, not in the decode, right? Not in the decode. So let's not get confused on that. This one's a bit easy to get confused. So sometimes little errors actually help us to understand things better, right? But that's kind of just a little error there. The getting the ingredients should be down here in the execute. Okay. And yeah, that's it. And I have got another question. Fetching is getting the instruction from the memory and decoding it. You see, there's two parts to that, right? Oh, well, decoding's been separated here. We should have four things here, I suppose. But yeah, it's getting the instruction from the memory. There we go, fetch and decode. All right, so I'm going to stop there recording. You guys might want to take a break for a minute. It won't be long. So if you want to take a break, get up and go for a walk. Don't go too far because I'll only be a minute. Faisal and Sammy and Uzaifa, I'm going to come back. All right, so it'll only be a minute and then we'll come back.